Liquid-liquid extraction is a separation technique that involves partitioning components in a mixture between two immiscible phases, that is, two liquids that don't dissolve in each other and form two separate phases when mixed, like gasoline and water or oil and vinegar. In a successful extraction, you take advantage of a difference in solubility between components in the mixture that would allow one component to pass selectively from one phase to another. In this example of a two-component mixture with components A and B, B is more soluble in phase 2 and A is more soluble in phase 1. Therefore, B passes selectively into phase 2. Since the two phases are physically distinct and mechanically separable, simply separating the layers after the extraction would afford physical separation of the two components. In the lab, liquid-liquid extractions are carried out by placing the two immiscible layers in a separatory funnel, which has openings at each end for admitting and releasing the liquid phases. Separatory funnels are specifically designed for the liquid-liquid extraction process, which involves the vigorous mixing and eventual separation of the two immiscible liquids. They come in slightly different shapes and sizes, but each has a stopcock at one end that permits the careful and controlled draining of the lower phase, or layer, from the separatory funnel. You'll be using a separatory funnel with a Teflon stopcock, which consists of the four components shown here. The stopcock in this photo is pictured in the open position, where liquid in the funnel passes through a narrow opening drilled through the Teflon. The opening is parallel with the stopcock handles, so anytime the handle is aligned with the north-south axis, you know it's open and liquid will drain through. In this photo of the stopcock in the closed position, the handles are parallel with the benchtop and you can clearly see the drilled opening in the Teflon. What follows is a demonstration of some general rules of use when handling separatory funnels during a liquid-liquid extraction. Always rest a separatory funnel that contains liquid in an iron ring that's firmly secured to a ring stand. Never prop it up in any other way or lay it on the benchtop, or it may spill its contents. If your funnel is too narrow to be supported by the iron ring and it passes completely through, short pieces of split rubber tubing are available in the lab that can be placed on the iron ring as shown here. No more than 2 should be needed. They narrow the opening of the ring just enough for the funnel to be securely supported. You should lightly grease the glass stopper with 3 or 4 small dollops of grease at points well separated from each other near the top of the stopper. Don't squeeze the tube of grease like a tube of toothpaste. Use an applicator stick to have better control of the amount being transferred to the glass. If you use way too much grease, it can work its way to the inner surface of the funnel and contaminate your sample. You grease the stopper to seal the connection and to prevent the stopper from being permanently attached to the funnel. The grease can dissolve in certain solvents and aqueous solutions, and you might need to reapply it during your liquid-liquid extraction. Since the funnel's glass stopper will be contaminated with grease and chemicals from the funnel, rest it on a watch glass, plastic weighing vessel, or some other surface instead of placing it directly on the benchtop or on top of your lab notebook. If you forget to close the stopcock when filling the funnel, the contents will immediately pass through the funnel onto the ring stand or benchtop. To avoid such mishaps, always place a clean receptacle underneath when filling the funnel to catch any liquid that might pass through the stopcock or be spilled when pouring. To avoid spills when draining liquid through the stopcock into a receiving vessel, such as an Erlenmeyer flask, place the tip of the funnel's stem below the lip of the receiving flask. If the flask accidentally moves a bit, the stem will still direct the draining liquid into the flask. When you pick up the funnel with the stopcock on the same side as your dominant hand, the one you'll use to open and close it when venting the funnel, you'll find that the stopcock ends up on the opposite side when you invert it, making it awkward to open and close the stopcock. To avoid this, before you pick up the funnel, turn it so the stopcock is facing away from your dominant hand. Consequently, when you pick it up and invert it, the stopcock will now be facing your dominant hand, and you can now open and close it more easily. The stopper must be pushed firmly into the ground glass joint when you hold the funnel, which can be done in different ways. You could secure the stopper in the palm of your hand while grasping the body of the funnel with your fingers when you shake it and vent vapors through the stopcock to release any pressure built up within. Or you could secure the stopper by placing it in the bend between palm and fingers and then grasp the neck of the joint with your fingers as you shake and vent the funnel during the process of extraction. Or secure the stopper with one or two of your fingers while grasping the body of the funnel with your other fingers. How you hold the funnel depends on your hand size and finger length, and you should practice this with an empty funnel to find the way that best suits you. When you're done shaking and venting the funnel, place it back in the iron ring and then turn it so the stopcock handle is facing your dominant hand, making it easier for you to drain liquid from the funnel. Remember to remove the stopper from the funnel when draining liquid through the stopcock. If it's not removed, a vacuum will form above the draining liquid since no air is being admitted to the funnel to replace the volume of liquid being displaced. The vacuum slows the rate of draining and it will eventually stop. It will only start again when the stopper is removed. To drain, turn the stopcock in a clockwise direction so you can see the hole in the stopcock approaching the hole in the separatory funnel. And when you close the stopcock, turn it counterclockwise to bring the hole back into your line of vision. If you perform this operation in the opposite way, that is counterclockwise to open followed by clockwise to close, the stopcock hole will approach the hole in the separatory funnel from the back side of the funnel where you can't see it. The flow will be more difficult to control, making separation of layers more difficult. Drain just to the point that the phase separation line is caught in the stopcock hole or stops just above the hole. Acid-base extraction is a type of liquid-liquid extraction used to separate mixtures of organic acids and bases. In their neutral form, organic acids and bases are generally soluble in organic solvents, such as diethyl ether. Selective conversion of one component in a mixture to its corresponding salt will allow that compound to pass selectively into the aqueous phase, since the salt is an ionic compound and soluble in water, but not soluble in ether. In the demonstration that follows, a mixture of benzoic acid, which is a carboxylic acid with a pKa of 4.2, and 2-naphthol, a phenol with a pKa of 9.5, is dissolved in the organic solvent diethyl ether, known simply as ether. When the ether solution is placed in a separatory funnel, along with an aqueous solution of the base sodium bicarbonate, benzoic acid, which is more acidic than 2-naphthol, is selectively deprotonated by the base, which converts benzoic acid to its corresponding sodium salt. The salt is insoluble in ether, but soluble in water, so it passes into the aqueous layer, leaving 2-naphthol behind in the ether layer. You'll be given a mixture of benzoic acid and 2-naphthol that you must separate by acid-base extraction. In this demo, the mixture is, by weight, 77% benzoic acid and 23% 2-naphthol. 1.3 grams of that mixture is weighed out. The mixture is then transferred to a 125 milliliter Erlenmeyer flask. "25 milliliters of diethyl ether are added to the flask. The flask is then corked and the contents are gently swirled. In a few moments, all solids dissolve to afford a clear, slightly tinted solution, as shown here. The ether solution of benzoic acid and 2-naphthol is then transferred to a clean separatory funnel. To the separatory funnel is added 15 milliliters of an aqueous solution of sodium bicarbonate. Here you can clearly see the two phases in the funnel, the top ether layer containing the two organic components and the bottom aqueous or water layer containing the base sodium bicarbonate. The funnel is then securely stoppered, inverted, and the stopcock is immediately opened to release pressure built up in the funnel. Frequent repeated venting of the funnel in this way over the course of the extraction is necessary to avoid so much pressure building up in the funnel that the stopper is pushed out, resulting in the contents of the funnel ending up on the bench top. The pressure can be caused by vapors from low-boiling solvents such as ether or dichloromethane, or, as in this case, carbon dioxide gas formed by reaction of bicarbonate with the carboxylic acid. Carelessness at this stage is the most common cause for product loss in this experiment, so remember to vent frequently, especially at the early stages of the extraction with bicarbonate. Vigorously shake and vent the flask as shown here for approximately 5 minutes. After you're finished shaking and venting the funnel, rest it in the iron ring. The two layers should separate within the funnel relatively quickly. Remove the glass stopper and prepare to drain the lower aqueous phase into a 125 ml Erlenmeyer flask labeled sodium bicarbonate layers. With the stopper removed, you can now drain the lower aqueous layer, leaving behind the upper organic layer. Be careful not to let any of the organic layer drain out with the lower layer. After draining the funnel, set aside the flask containing the first sodium bicarbonate aqueous layer. Obtain another 15 milliliters of fresh aqueous sodium bicarbonate from a stock bottle and add it to the funnel. You'll use this second portion to perform a second extraction on the organic layer that you left in the separatory funnel. Shake and frequently vent the securely stoppered funnel for approximately 5 minutes in the same way you did before. After approximately 5 minutes, stop shaking and venting the funnel. Notice how quickly the two layers separate within the funnel. Now rest the funnel in the iron ring and prepare to drain the lower aqueous layer away from the upper organic layer. You'll combine this second sodium bicarbonate aqueous layer with the first sodium bicarbonate aqueous layer in the flask labeled sodium bicarbonate layers. Once again, carefully drain the lower aqueous layer from the funnel, leaving behind the upper organic layer. Be sure to close the stopcock just before the organic layer begins to enter it. The flask labeled sodium bicarbonate layers contains the sodium salt of benzoic acid and unreacted sodium bicarbonate. Leave the flask uncorked and place it in a safe spot in your hood. With benzoic acid having been selectively removed by the bicarbonate extractions, The ether solution in the separatory funnel now contains only 2 naphthol and possibly a small amount of organic impurities. When an aqueous solution of the base sodium hydroxide is added to the funnel, followed by shaking and venting the funnel contents, the 2 naphthol present in the ether layer is deprotonated by the base, which converts it to its corresponding sodium salt. Since the salt is insoluble in ether and soluble in water, it passes from the ether layer into the lower water layer, leaving behind in the organic layer any non-acidic organic impurities that were present in the mixture. To extract the 2 naphthol from the organic layer, you will use one single 20 ml portion of an aqueous solution of sodium hydroxide. Add the sodium hydroxide to the organic layer in the separatory funnel. Stopper it securely. Then shake and vent the funnel in the usual manner for a liquid-liquid extraction. Continue to shake and vent the funnel for approximately 5 minutes. After you finish shaking and venting the funnel, be prepared to drain the lower aqueous phase into a 125 ml Erlenmeyer flask labeled sodium hydroxide layer. With the stopper removed, you can now begin to drain the lower aqueous layer. Be careful not to let any of the organic layer drain out with the lower layer. After draining the lower layer, set aside the flask labeled sodium hydroxide layer. Then pour the organic layer through the upper opening of the funnel into a 50 ml Erlenmeyer flask labeled organic layer. Cork it, then set it aside for proper disposal in an organic waste container at the end of the experiment. At this point, the sodium salts of benzoic acid and 2-naphthol must be converted back to benzoic acid and 2-naphthol themselves, and the 2 solid products must be isolated from solution. The conversion of these sodium salts back to benzoic acid and 2-naphthol is accomplished by acidifying the contents of the flasks labeled sodium bicarbonate layers and sodium hydroxide layer by addition of a concentrated acid, in this case concentrated HCl. The acid neutralizes the remaining base and protonates the organic anions. Although the salts of benzoic acid and 2-naphthol are water-soluble, benzoic acid and 2-naphthol themselves are not, and they immediately precipitate from the acidified aqueous solutions. Place 10 milliliters of concentrated HCl in a clean and dry 10 milliliter graduated cylinder and clamp it securely so that it doesn't tip over. You'll use a long stem pasture pipette to transfer the concentrated HCl. Insert the pipette a short distance into the bulb and then give it a brief tug to confirm it's secure. As you can see here, the pipette is firmly attached to the bulb and it won't come loose. Remember, concentrated HCl is very corrosive, so always stand the pipette in a tall flask or beaker and don't lay it on the bench top or on any other surface. Acidify the aqueous solution in the 125 ml Erlenmeyer flask labeled sodium bicarbonate layers by addition of concentrated HCl in several small portions with periodic swirling. Note, Carbon dioxide is a byproduct in the reaction of HCl with sodium bicarbonate, and foaming will occur when HCl reacts with the unreacted sodium bicarbonate in the flask. Initially add concentrated HCl in small portions while swirling the flask contents to avoid having your product spill all over the bench top. After initial frothing subsides, you can add the HCl in larger portions. The white solid you see is benzoic acid. Note how it goes back into solution upon swirling. That's because the solution is still not acidic, and the precipitated acid is being converted back to its salt by reaction with sodium bicarbonate that's still present. You must continue to add acid until the white precipitate of benzoic acid persists. You can see that the white solid is no longer redissolving. Add another 1 to 2 milliliters of concentrated acid to make sure that the solution is acidic. The addition of excess concentrated HCl will not harm the benzoic acid. Rest the pipette in the flask and not on the bench top. You should always confirm the acidity of aqueous solutions with either pH paper or litmus paper. In this instance, we're using litmus paper. Note how this piece of blue litmus paper turns red upon addition of concentrated HCl, indicating that we want to use blue litmus paper to test the acidity of our aqueous solution. Don't dip the litmus paper into the solution being tested. You should always use either a glass rod or a spatula to capture a small amount of the liquid and then bring that captured liquid to the litmus paper. You can see that the aqueous solution has turned the blue litmus paper red, confirming that the solution is acidic, as expected by the persistence of the benzoic acid precipitate. Now acidify the contents of the flask labeled sodium hydroxide layer. Don't forget to note the amounts of HCl that you're using for each acidification. Since CO2 is not being generated in this acidification, you should not expect to see foaming or frothing in the flask. The precipitated solid no longer redissolves, indicating that the solution is most likely acidic. As before, add an additional 1 or 2 mils of concentrated HCl to make sure that the solution is acidic. The same piece of blue litmus paper can be used to test the acidity of this solution. The glass rod is cleaned with fresh tap water to remove any residual acid before use. The test with litmus paper confirms the acidity of the aqueous solution. Each precipitated product must be collected by vacuum filtration. Before setting up for vacuum filtration, the flask containing precipitated benzoic acid is cooled in an ice water bath for approximately 5 minutes, since benzoic acid is very slightly soluble in room temperature water, with a solubility of approximately 30 milligrams for every 10 milliliters of water. Place the corked flask in a vessel tall enough to prevent it from being tipped over, then add ice, followed by enough water to be at a level slightly higher than the height of the liquid in the flask being cooled. The flask containing precipitated 2-naphthol is not cooled in ice water, since 2-naphthol is much less soluble in room temperature water than benzoic acid. A demonstration on how to properly set up a vacuum filtration apparatus is included in the demo video on recrystallization. Place a single piece of filter paper into the Buchner funnel. Make sure it completely covers the holes in the funnel, but is not so big that it rides up the inner sides of the funnel. Open the valve leading to the vacuum source, and then pinch off the small tubing on the 3-way plastic connector of the trap to close off the system and create a vacuum. Since much of the solid is resting at the bottom and sides of the flask, swirl the flask's contents to resuspend the solid so that it comes out with the liquid as you pour it into the Buchner funnel. Use a small volume of cold water to resuspend the solid remaining in the flask. You can use a spatula to dislodge and resuspend the solid that adheres to the inner walls of the flask. If solid still remains in the flask, you can repeat the process. Momentarily break the vacuum to allow the liquid to thoroughly rinse the filtrate off the solid collected in the funnel. Then reapply vacuum to remove the rinse. Don't be concerned about any small amount of solid still visible on the inner walls of the flask, as its weight is negligible. In a few moments, you'll notice very little liquid entering the flask from the Buchner funnel, and you can now break the vacuum. Please remember to close the valve to the vacuum source as soon as you've finished using it. In the Buchner funnel, you will find a compact white solid, which is benzoic acid. Transfer the entire damp sample along with filter paper into a weighing vessel for temporary storage until the entire sample has completely dried. Since you'll be using this apparatus again to collect the 2-Naphthol from solution, thoroughly clean both the Buchner funnel and the filter flask before proceeding. The aqueous filtrate can be discarded in a fume hood sink. Having cleaned the Buchner funnel and the filter flask, you're now ready to collect 2-Naphthol using a fresh piece of filter paper. As before, swirl the contents of the flask to resuspend the solid before pouring the contents into the Buchner funnel. Use a small amount of fresh water to help transfer any solid that remains in the flask. The vacuum is momentarily broken to allow the water to thoroughly rinse the solid in the funnel. Very little liquid is entering the flask from the Buchner funnel, so you can now break the vacuum. Remember to close the valve to the vacuum source as soon as you finish using it. The compact solid in the Buchner funnel is 2-Naphthol. As you did with benzoic acid, transfer the entire damp sample of 2-Naphthol along with filter paper into a weighing vessel for temporary storage until the entire sample has completely dried. At this point, don't attempt to dislodge any solid that adheres to the filter paper. When both solid and filter paper are completely dry, they will easily separate. Sample drying times vary, but allowing these samples to air dry overnight should be sufficient, at which point you can weigh the samples and determine their melting point ranges.